Hello and welcome to another day of Advent of Code. This is day 15, which has another number counting puzzle sort of thing. Let's jump into it. Okay, so the puzzle for today is a series of numbers that seed the elves' number game. This number game actually has a name. It's some series. I don't remember the name though. And it's not important to actually solving the problem, unless you want to solve it the super fast way, which we're not going to go over in this video because I think solving it I know this silly math trick is not actually, that interesting to solving these problems. But anyway, the input looks like this. It's on one line and it has a series of comma-separated numbers, and we're going to parse that into a list of integers. And the way this game works is for the first few turns, the elves in turn will say out each of the numbers. So turn 1, they'll say 0, turn 2, they'll say 3, turn 3, they'll say 6. After that, and this is where I got super confused implementing this live. After that, they will say a specific number based on the number of the previous turn. So you have to basically keep track of whatever the previous turn was. And if the previous number was said for the absolute first time, let's just say for the first time, then you will say 0, and that actually counts as saying 0, so you'll have to record that you said 0 as well. Otherwise, if that number has been said before, say the difference between the turn counts on which it was said before. So you basically have to keep track of at least the last 2 times that something was said. And that's how it works. Part 1 is what is the 20/20th number, and part 2 doesn't add any new constraints. It just increases the number to 30 million. Now, when I was solving this problem and I saw 30 million, I was like, that's not a very big number, and so there must be some trick. But it turns out you can still solve this 30 millionth number in about 10 seconds, or about 30 seconds in Python. So I didn't actually bother optimizing my solution at all, and I'll show you kind of my basic solution and some ways that we might be able to improve it if we wanted to, but we don't really need to. But anyway, let's start with the parsing. Parsing's pretty easy. Return int s, or int, I don't know, n for n in s.strip, because we're going to remove all the white space here, and then we're going to split on commas. Split on comma. And if we run this, yes, save that, yes. Parsing.py, you'll see, pretty simple parse. We just turn it into a list. So let's jump into part 1 and part 2 at the same time, since they are not a different problem this time. And we're gonna have a compute function. So when I saw this, like what is the 20/20th turns number, what I jumped to immediately is looping over a range, so for turn in range 2020. However, in this case, we're going to take a parameter in that's going to represent how far we're going. So we'll put, n in here, and we need to satisfy these rules. So the first set is for the first turns, say the number in the seed. And so we know the turn number and we know the length of these numbers, so we can just say, if len of, if turn is less than len of numbers, then n equals numbers at turn. So this is just going to select the number that they're going to say from this list of numbers. This is how we handle the preamble. Then we need to handle the rest of this. If the previous number is said for the first time, say 0. Otherwise, say the difference between the previous turn and that turn. Okay, so we need to record all of the turns that things are being said. And so what I did for this, just as like I'm not going to try and optimize this at all. I'm just going to record all the turns that things are said at. And it turns out that it's actually fast enough to do that. So what I did was say that the previous seen things was a dictionary that mapped the integer to a list of turn counts. Now we can use default dict here to make this a little bit easier. Collections.defaultDict, and I'm going to use default dict list. What this does, and again, I'll link a video about default dict if you haven't gotten tired of me linking the default dict video. But what this does is it allows us to just, access values in this dictionary without making sure that they're there first. So we'll always get at least an empty list whenever we try and access into this mapping here. And so this makes it really easy to just append numbers without really thinking about it. But let's implement the next check here. So the next check is if this is the first time this number was said, so the previous loop was the first time it had ever been run, we're going to check if the length of that, I guess we also need to append down here. Let's append first. Prev scene for n dot append turn. That way we have our turn, put into this after it. So when we run this loop for the next time, we will have at least one item always for the previous number. So we can say else if the length of prev scene n is equal to 1, so this means it was said for the first time, then we know that n is 0. And then the last case is we've seen it, well, we're not in the preamble, we've seen it at least one time, so we're going to say the difference between the previous turn and the previous turn. So what we're going to do here is n equals prev scene n -1, so this will get us the previous turn that it was said, minus prev scene n -2. Now you'll notice here that I am continually appending to this list, and we're only ever accessing the last two items. So there is an optimization here where you don't bother to do, you don't keep everything forever, because there's no reason to keep everything forever. But it actually doesn't matter in this case. It's fast enough without optimizing there. And then, oh, this should have been indented. Oops. And then finally, the last part is just return n. So after this loop is run, we'll know the n that was said on the very last turn. And so we can just say return n. And, oh, it didn't keep track of the expected values here. Let me, day 15, part 1. Okay, so the first one we should expect 436, and for the really, really long one, 2.pi, we should expect this number. And you'll notice when I run this that it lags significantly. So my solution is not that fast, but it is fast enough to actually solve the problem. So you can see the 2020, that got spit out really, really quickly. We answered that one, super fast. But this solution is not so optimized for for the sake of this problem, but it is fast enough to complete within, about 30 seconds-ish. So we'll see an answer here. An interesting thing here is PyPy, which is an alternative implementation of Python. Let's actually put this over here so we can watch the two run. PyPy actually answers this question relatively quickly. And what PyPy is it's a just-in-time compiled version of Python, where it will, yeah, you can see PyPy's already done, where it'll basically optimize pure Python code on the fly and, answer this question a lot quicker. In fact, I think I got it down. Even with this unoptimized solution, PyPy is able to answer this in like, I don't know, 10 seconds-ish, whereas CPython took like 40 seconds. Yes, 7.5 seconds, which is, not the fastest, but it's pretty good for for our purposes here. But anyway, let's talk about algorithmic efficiency here. The first thing that we're talking about here is this is ON, so this is linear on the size of our input. However, we're doing, a lot of work with this append here, and we're keeping a lot of data around. So this is pretty expensive here, and memory is actually growing continuously as we go. We don't actually need to keep track of all of the numbers that we, put into here. We could replace this with, for instance, a bounded queue. So you could use, lambda collections.dec max len equals 2. And that would give you a bounded queue. So if you insert something, it'll just kick one off at the end, and it'll always keep only 2 values around. Now, when I tried this, this actually made the problem slower. So just like the dumb list solution is actually faster. And this is kind of a good piece of advice here. Like, don't try and micro-optimize stuff unless you have performance data backing it up. Because in theory, this is much faster, but in practice, it's almost twice as slow. So I don't really have a good explanation for why it's twice as slow. But, this solution works, so run with it. But hopefully this was helpful. Hopefully I showed you some kind of neat things. And if nothing else, I showed you Dec, which is, a kind of interesting data type. But anyway, I'll see you in the next one.